So, what are the major players shaping the migration of humans? What factors are most important, such as climate change, the characteristics of dispersion, interbreeding, or competition? To address these issues, we're going to employ a simple population dynamics model in a simple domain. I like simple because it's easier to get to grips with the underlying dynamics of the system, and hopefully one can make statements about how more complex systems in more complex domains operate, and maybe shape the numerical experimentation that is done. So, as is suggested from this figure, we're going to, for this talk, we're going to concentrate on Homo sapien migrations into Western Europe. According to this figure, which was produced by Paul Mellers, there are two principal routes. The blue route, which takes us along the Mediterranean coast, and the green route that makes use of the river Danube, taking individuals to northwest Europe. This figure was redrawn by Paul Mellers after the redating of KC4, which was found in Kent's Cavern, which incidentally should be a little bit further west than indicated here, giving a date of around about 42,000 years. He also included the how do you pronounce that? Ulozilian sites, but it's my understanding that there's still uncertainty exactly how this techno-complex got into southern Europe, and in particular Italy. While this was happening, of course, we know that there was climate variability, in particular these Dansgaard-Oeschger events with rapid warming and slower cooling in the system, and how much this influences the migration of Homo sapiens during this period needs to be assessed. So, we're going to concentrate on Homo sapiens arriving in northwest Europe during this time of climate variability. And looking at the techno-complexes, it appears that there were at least two waves. One that arrived around about 45,000 years ago, where, as we have already seen, this is a time when Neanderthals and the Homo sapiens coexist. And a second wave involving a different techno-complex, which arrived around about 40,000 years ago and sort of coincides with the extinction of Neanderthals. One important question is, although there is climate variability, how important are these Dansgaard-Oeschger events on this development? I said we're going to use a relatively simple population dynamics model. What we have here are equations for the populations of Homo sapiens and Neanderthals. Changes in these populations is given by the difference between growth and mortality. And we're going to let the populations diffuse. The two populations are connected and interact through competition, given by the competition coefficients alpha ij. And they also interbreed. And here we take notice of the fact that during this time, it is thought that the gene flow was from Neanderthals into Homo sapiens, in other words, Neanderthals being assimilated into the Homo sapien population. And so the interbreeding is going to take individuals from Neanderthals and place them in the Homo sapien population. The combination of limited growth, such as here, and dispersion will produce wave fronts that propagate at a given speed, and the characteristics of that wave front will depend upon how we model the dispersion. For Neanderthals, we're going to assume that they undertake normal diffusion, so the exponent here is factor 2. But for the Homo sapiens, we're going to recognize that maybe they're more adventurous, and there's evidence that suggests that the Homo sapiens coming out of Africa had a so-called novelty-seeking gene, which is an allele of the dopamine receptor D4, which makes them more adventurous. Now, novelty-seeking genes are important in a number of instances, and as this paper suggests, being bolder, can you take everything? If you get there first, it certainly helps. And these behavioral characteristics are subject to polymorphisms, include exploration, activity, boldness, all of which would contribute to being more adventurous. So this is our simple domain. So you can assume that this is Istanbul, and this is either northwest Europe or southeast Europe. The distance here is 2,000 kilometers, which is comparable to that distance. I should say that both the distances and the time can be rescaled if you dislike 2,000 kilometers, or if you dislike the rate at which time is changing here, by rescaling the growth rate and the diffusion coefficient, but keeping the dynamics the same. So we're going to start off with, so here the red line gives us the population of Neanderthals. The blue line gives us the population of Homo sapiens. Before the Homo sapiens arrive, then the Neanderthals are happy and living at a given density across the width of this domain. And these two simulations are going to vary depending on the interbreeding rate. So we've chosen a relatively low interbreeding rate, again indicative of the fact that populations are somewhat isolated and interact only occasionally. So around about 2%. The bottom one is when we increase the interbreeding rate to 3%. So let's see what happens. We see that the Homo sapien population increases. In this particular case, with a smaller value for the interbreeding rate, we get into a state where there's coexistence. Whereas if the interbreeding rate is a little bit larger, then the Neanderthals are no longer allowed to exist and go extinct across the domain. And if we look at the rate at which the front of Homo sapiens propagates across the domain, you may have noticed that there was an acceleration in that front. the solid blue line here gives us the position and the speed of the Homo sapien front, and we see that the front is accelerating with time. The other, it will keep accelerating until, if we extended the domain, then we limit the acceleration and get a maximum speed of order 14 kilometers per year, which is perhaps a little bit unrealistic. The other way we can limit the acceleration is by having the growth rate decreasing with x, which is relevant to the experiment that we're going to look at next. So if things are if the growth rate is decreasing with distance along the domain, then that acceleration ceases, and in fact the front starts to get slower. Okay, so this is our climate model. As I said, things are nice and simple, and we're going to express the impact of climate on the growth rate of a population. Now, because we have explicit mortality, that is the same as changing the carrying capacity. So a decreasing growth rate will reduce the carrying capacity of the domain. And we're going to note that during Dansgaard-Oeschger cycles, the climate in Europe during interstadials is comparatively mild and moist compared with the cold and drier stadal conditions. And in particular, during these cold events, the winters in northwest Europe are particularly harsh. The biggest change in the climate is in northwest Europe. So we're going to take account of that by changing the growth rate of both Homo sapiens and Neanderthals in the far northwest of our domain. Now, Neanderthals, as was already been mentioned, have gone through many of these cycles already and therefore are able to cope with the changing climate. But so we're going to put a limited reduction in the growth rate for Neanderthals. Homo sapiens, however, are coming from a warmer climate and therefore may not be that well adapted to the harsher winters during a cold event. And in this particular case, we're going to put the effective growth rate to be negative. In other words, the individuals would die out with time. And we're going to reduce the change in the growth rate as we go towards the southeast. Our Dansgaard-Oeschger oscillations, which is how the growth rates are varying in the far northwest, look like this. We have a very rapid increase in the growth rate and then a slower decrease as the climate cools. And note, because we're assuming that the Homo sapiens are not adapted at all to these colder conditions, there's a significant time when their effective growth rate is less than that of Neanderthals. So that is our climate model. So we're going to look at three conditions. The center animation here is what we've just talked about, where there's this rather large variation in growth rate associated with the Dansgaard-Oeschger events. The top one is if we have no Dansgaard-Oeschger events. In other words, it remains cold with harsh winters in the far northwest. And the lower panel is if the Homo sapiens are better adapted. So now, although there's a larger reduction in larger reduction in the growth rate. It's not as much as it was before, and in fact, here we keep the effective growth rate of Homo sapiens to be the same as that of Neanderthals. Now I'm going to start all of these together, so it's a little bit difficult to follow each of them, but I suggest you look predominantly at the center animation here, which is with the Dansgaard-Oeschger oscillations. So as before, we see a front of Homo sapiens propagating across the domain, leaving a coexistence in all three cases. But because it's much colder here, the Homo sapiens almost go extinct, but get revived when things get warmer, so that rather than the Homo sapiens go extinct, the climate variations are aiding their existence throughout time. When there's no climate variability, the front of Homo sapiens slows, and it slows such that it comes to a halt around about here, where northwest of this point, the Homo sapiens do not survive. If the Homo sapiens are better adapted, in the warm periods, we get coexistence between Homo sapiens and Neanderthals. But as we will see a little bit later, if the Neanderthal population gets too small, then they go extinct, and we're left with this slab of Neanderthals in the far southeast corner. Things have stopped here, but if you had been looking, you would see that this front between coexistence and extinction is slowly propagating towards the southeast, and will eventually end up with a state where there are no Neanderthals. In the last animation, we'll look at a similar situation. So I'm running out of time already. So I thought I will just skip ahead and look at here. There's a series of phase portraits that tell us something about the dynamics of the system, at least the reactive part of the system. If the Homo sapiens are better adapted because of interbreeding, they in the cold period they dominate, and the Neanderthals will go extinct. The individual arrows here show the direction that the solution will take from a given point in Homo sapien Neanderthal space. As you can see, these arrows are all pointing towards this red dot, and that red dot is a stable equilibrium. If we reduce the interbreeding, in this case we're halving it, then bifurcation takes place, and a stable attracting node and an unstable saddle node appear, which separate as we decrease the interbreeding rate. And associated with this saddle node, there's what is known as a stable manifold, a separatrix, which is repelling. And it depends critically on what side of this stable manifold one is. If you start this side of the stable manifold, then you end up at this coexistence point. if you start at this side of the stable manifold, then you end up with the Neanderthals going extinct, and we only have Homo sapiens. This is very much likened to what has been speculated in terms of why the Neanderthals went extinct, in that if the population of the Neanderthals get too small, then interbreeding or assimilation of Neanderthals into Homo sapiens will lead to the demise of the Neanderthals. So the take-home message here is that we hope that the approach that is used allows a quantitative assessment of important processes and puts bounds on parameters and rates. It's important to consider the spatial and temporal variations of the habitat. We haven't really looked at it, but this having an adventure-seeking gene can be very beneficial in times of climate change, and in particular if we get a front between two populations. The dynamics of that front depend critically on whether or not one or more of the populations have this adventure-seeking gene. And although we skipped through things, we've chosen model settings that are sufficient to account for the inferred impact of modern human migration, in the sense that the first wave of Homo sapiens survives only because of the climate variation, and we get coexistence. The second wave, where the technology has improved and the Homo sapiens are better adapted, then we find that the Neanderthals go extinct. But I do stress that this is only sufficient, and we can construct things so that although we get coexistence and then extinction, where that does not involve climate variability, and it does not involve interbreeding. How we go about deciding which of those, or if both of those are relevant, remains to be seen, and I welcome any comments on that regard. Thank you.